All right, so we're going to do some more complicated examples of chapter 7. I got one from your homework, one that perhaps is related to a more complicated homework question. Okay, so the first one is really going to test our ability to draw a correct free body diagram, to sum the correct forces, and ultimately to go through all of the machinery to get a correct answer of Newton's third law. The second example is a little bit more tricky because pulleys can get kind of subtle. So actually, I'll do 3 examples. The second example will be kind of in the middle, and the third one, if we have time, will be the harder one. Okay. Perfect. So let's get going on this. The first example is number 34. Okay, I'm gonna okay, so I'm not gonna really be checking the chat right now. It's number 734, and what we've got in this problem is a setup here where we got 2 blocks. And this is a 1 kilogram block and a 2 kilogram block. And there's a rope between them, and it's on a rough surface. But the thing about this rough surface is that each of the blocks make a different coefficient with the surface. This, let's call the back one M sub 1. This makes a mu sub 1 equals 0.2. And this one in the front makes a mu sub 1 equals 0.10. Okay, again, mu sub k is a coefficient of kinetic friction between the surface and the block. Okay. So before I move on, any questions or comments on any part of what I've done? Okay. Answer in chat. Chapter 8 moved to chapter 8's moved to next week, and chapter 7 is moved to tomorrow. Okay. So just in case, certainly welcome to unmute. I hear someone that doesn't sound like they're unmuted, so background noise. Oops. Okay, you can certainly unmute at any time, but I'm going to go ahead and mute everyone just to make the video a little nicer. All right. Let me go back to my recording. Oh, I guess I wasn't stopped. So I'll just keep going. So now how do I solve this thing for A and T? I think the best way to do it would be to remind yourself how to do friction in each of these X equations. And then perhaps maybe adding the equations together. That would give you sufficient stuff to solve for A. Subtracting the equations isn't that easy, or it's not easy to, what am I trying to say? It's not so easy just to subtract the 2 equations. You need to solve both of them for A before you do that. But yeah, I think the best way to solve this for A and T would be take 1 sub x, take 2 sub x, plug in the expressions for friction in both the examples, and then subtract. And so I think I will do that on a different page. I'm getting worried about the amount of space that I might not have. So I have this JPEG saved, certainly this being recorded anyway, but I'll save this and start it. Okay, so if I take 1x and 1y themselves and plug in the values for friction, what am I going to get? Two big equations. Okay, 1x, I will get plus m1g sine of theta plus t minus, now this is where I plug in friction, mu sub 1 m1 g cosine theta equals plus m1a. So that is the expression for 1x with friction included, right? Because 1y gave us the expression for the normal force being N equals N sub 1 equals M sub 1g plus cosine theta. And then the friction equation is just friction equals coefficient times normal. So that's the first one. What's the second one? 2 sub x. And you'll see very quickly how we can just eliminate tension. This will be plus m2g sine of theta. Lucky for us, the angles are the same. Minus t minus mu sub 2 m2g sine theta equals plus m sub 2a. So those are the two equations with the friction substituted in. And so now you can obviously see that we can eliminate tension just by adding the equations. And it's going to be a big mess, but a mess in the sense that it's good practice for you. So adding 1x and 2x. What are we going to get? Well, the accelerations are going to cancel. And we want to get as much stuff combined as we can. Right, so adding those two together. The t's cancel. What happens to this stuff in the front? It's just m1 plus m2, g sine theta. Let's see, you'll get, we'll double check this, but it'll be m1 plus m2 g sine theta, right? The tensions cancel. Now what about the frictions? It'll be minus mu sub 1 m1 plus mu sub 2 m2 g cosine theta equals m1 plus m2 times a. All right, let's take a look. We got adding those two terms. Yeah, they both have a g sine theta in them. So factor out the g sine theta, you just get m1 plus m2. T's cancel. Did we do the coefficient friction right? Factor out a g cosine. Oh, did I write that wrong? Yeah, there's an error right there. This should be, I'll even do this. Let's see. Oops. Oh, shortcut. Just a minute. Yeah, there was an error right there. So certainly correct that. So use different color. This should be cosine. So that's a correction there. And if I was being cute, I would say -1, but okay, just take it off. Right, so we have mu1 m1 plus mu2 m2 g cosine theta equals m1 plus m2a. And so now we can divide and find our result for acceleration, which it's striking the results. We get a equals, let's see, acceleration. Okay, now that we have let's write the final value of the acceleration. Perfect. So we got A. Now, the M1 plus M2 will cancel with this term, and so we're going to get G sine theta. Pretty interesting result. G sine theta minus mu1 m1 plus mu2 m2 over m1 plus m2 times g cosine theta. And in fact, that g still being in there even bothers me still, and so I would even just factor it out and just get rid of that other one. And so that is the answer for friction. Or sorry, that's the answer for the acceleration. Notice, okay, this is a common thing that we do when we get an answer. We take some limiting cases to see what would happen. So first of all, if they're both 0, then what do we get? Well, then we get acceleration equals just g sine theta, as we would have expected, because they'd both be falling down the incline at a rate equal to just gravity. So that makes sense. That second term goes away. If they're non-zero but still equal, no, that didn't look very good. If they're non-zero and still equal, then what does the acceleration become? It's g sine theta minus mu g cosine theta, which that actually is the result, if you remember from chapter 6, that's the result of a block sliding down an incline on its own without anything else. And so the fact that we get these results is helpful to us. Okay, so that is acceleration. Do we want to try tension? I think we can. I think we can do tension still, or I think we can do tension as well. So what is tension then? Well, we still need, instead of adding these two equations together, let's solve both of them for A and then subtract them in a way that would be clever. Like I said, problems like this are probably about as complicated as you're going to get in this class, and it's if we only have time for one more small example, that's fine. But so if we were to subtract these two, let's solve it for A. Let's divide both sides by their respective masses first, and then subtract. What are we going to get? When we do that, it's actually probably get a homework exercise for you to do. I'll just do it on this side, just to finish the problem. So what I'm going to say is subtract equation 1x divided by m1 and equation 2x divided by m2. So that means if I divide the first 1x by m1, I'm going to get, g sine theta plus t over m equals mu1 g cosine theta equals a. And then same thing when I divide by m2. So when I do that, what am I going to get? Well, a lot of this stuff will cancel. The first terms will cancel, and I'll have plus t well, in these examples, I don't want to be advocating that we should do as little work as possible. Let's rewrite it out. So it'd be just g, so 1x would be g sine theta plus t over m1 minus mu1 g sine cos theta equals a. That'd be 1x divided by m, and then 2x divided by m2 is the same g sine theta minus t over m2 minus mu2 g cosine theta equals a. Yeah, so if I divide by the respective masses to solve for a in both of them, I mean, you could set them equal to each other as well, but subtracting them to me makes more sense because these are going to go away. So when you subtract these two equations, yeah, the A's are going to cancel. And so what you'll be left with? You'll be left with a T 1 over M1 plus 1 over M2. And then what happens here? We've got G sine theta. You got to make sure you get these minus signs right. We got a minus mu1. So it'll be mu2 minus mu1. Minus mu1 G cos theta equals 0. And solving this for t then, you can check for yourself. Whenever you have two 1 over reciprocals added together, that equals, the sum over the product. And so dividing that will give you the product over the sum. So ultimately you'll end up with this. Let's see. It'll be, we're almost done. Mu2 minus mu1 times M1, M2 over M1 plus M2 times G cos theta. And actually, these signs flip. It should be, so I have a mu2 minus mu1 here. Giving it to the other side will switch the directions of the signs. And so this result then should actually be mu1 minus mu2. Mu1 minus mu2. And that, in a very, overall way, that is the expression for tension. For the specific numbers in the problem, A is 2.12 meters per second squared, and T is 0.61 newtons. Those are the answers for number 34. So I guess if you had stayed and watched this entire video, you get the answer. But yeah, let's look at the formula for T and see if it makes sense. Once again, we see that first of all, this can only be positive. Okay? Tension can't be negative in this case, because that would mean that we're like pushing in on the rope, which the rope is defined to be flexible. But you also see the important thing is that you see this difference between the coefficients, right? If the coefficients are 0, there's no tension. If the coefficients are the same, there's also no tension. And the only way that there is a non-zero tension is if the block behind has a larger coefficient than the block in front. It doesn't necessarily matter on the mass because this is switched. This term is symmetric. If you flip the amounts of M1 and M2, it's unchanged. But it's the coefficients that matter for the tension. And I guess it depends on the angle in G as well. All right, so that is a very difficult Newton's third law problem, done more or less the entire way. We had a couple of roadblocks in between there, but that's the result. I'm going to save this as well. Okay, so, and then the last example is something that's a lot smaller, a lot less difficult equation-wise, but logically it can be kind of confusing. So in this last example, what's the setup? We have like a person like on roller skates. Okay, and the idea is that they are pulling on a rope that's attached to a pulley that then turns back around and it's attached to like their torso. So this is like the rock climbing problem or like something like that. Hopefully, okay. So the question is, what is the tension in the what's the tension in the rope, what's the acceleration of the person? So mass and what does a free body diagram look like? Okay, so let's make some numbers, some very easy numbers just to make this simple. So 100 kilogram person, I can do like 670 or so, maybe 80 kilograms. An 80 kilogram person, let's say you pull on it like a force of maybe like 40 pounds or so. That would be like a tension. Let's say there's a tension of like 100 newtons. That's about 20 pounds of force. I mean, we could even do more, 200 newtons. What's their acceleration? Well, compare that to the simple example with the no rope or with there's no pulley. Okay, if the person pulls on it and the rope is just attached to the wall, well, what you have is you just have in the horizontal direction, you have your normal and you have your gravity, but you got tension equals ma. So in this case, it'd be like, acceleration would be 200 over 80 meters per second squared, which is what? 2.5. 2.5 meters per second squared. So that's the simple case without a pulley. But what's the role of the pulley? This once again underscores the role that Newton's third law plays in these examples. Because when the person pulls on the rope, they feel a force at the point of contact equal to 200 newtons. But by the definition of tension and by the fact that it goes over the pulley, the other point of contact also feels that they feel another tension force at that point of contact. So, and it seems like you're getting something for nothing, but you're not, because in this free body diagram, it's the same normal, same gravity, but now you get two tensions. And here's the kicker, they're both 200 newtons. So by using the pulley and attaching the rope to the other side of the person's torso, they get double the force. And so now this will be 400 newtons equals ma. And so you actually get double the acceleration. You get 5.0 meters per second squared. The fact that that's connected to a rope. Okay, and so you can do these sorts of examples where you have a pulley that's connected to one of the objects that's moving can get kind of subtle. There's also a problem in the end of chapter where you have like a painter or something like on a platform and they're pulling on, well, I'll just sketch it out real quick. I mean, it's the painter on like a platform pulling on the rope, but the rope is attached to, the platform is attached. I'm not drawing this very well, but the rope is attached to the platform. And so how does this work? How does the person actually, what are we actually doing here? If you want, you can separate the system to be the platform and the painter, or the platform and the person. That actually doesn't matter. What matters is the fact that there's the platform pulley, or the pulley platform system, or the so many P's. The painter and platform system is pulling on the rope with the pulley. And so the system still gets double tension. Tension right here, tension right here. So a lot of times we define this as something called mechanical advantage or leverage or something like that. But those are the types of, more in-depth examples of Newton's third law that you need to look out for.